we're going to now talk about classification. So the big twist today is that we're moving away from predicting a continuous value to predicting something that is categorical, which is not really a big change if you think about it, but it leads to a whole genre of techniques in machine learning and statistics that are geared at trying to make predictions about things that are not quantitative but are categorical. So I actually want to step back and give you guys a bigger picture of machine learning techniques. This is useful when you encounter a problem to know which one of the places in this diagram you are in. So we've already talked about regression. I want to frame it in this context of supervised and unsupervised learning. So regression, we had a quantitative response variable. So we're thinking in this picture not necessarily about the features, but about the response, the thing we're trying to model. It is a form of supervised learning because in the training procedure you have y values. You have x, the features, and then the y, the label that you're trying to predict, the regression, the quantity you're trying to regress on. So supervised learning is a family of techniques that operate on labeled data. Today we're going to talk about classification, which is where we've moved again from a quantitative value to a categorical value. That's actually just one branch. There's another far other side of the picture, another extreme branch where I do not give you labels. I just give you x's. You can still learn with just x's. One thing you might do is you might do something like dimensionality reduction. This is saying I want to infer regressive quantities. I want to infer quantitative y values from data without ever seeing them. This is something like maybe a good intuition. When people analyze preferences, they look at the relationship between what people buy and the products that they buy. So you can build a graph. When I'm doing dimensionality reduction, I might take this complex representation of the things you bought and try to place them in a two-dimensional space, which would allow me to put people on a plane and group them into different parts of that space that would define similar characteristics. Right? So it's a way of taking a very complex high-dimensional x and predicting a lower-dimensional y that corresponds to each of those x values. Unfortunately, we do not have time in this class to go into dimensionality reduction. It is a widely used technique. You will see things like PCA. It's a pretty common tool in the dimensionality reduction space. You'll use techniques like singular value decomposition. If this is something you're interested in, stop by office hours, and I'd be happy to talk more about it. But it is a way of taking data that is not labeled and finding a simpler representation. Here's one more that you might see. You might take a bag of words model. So you have all these tweets. You want to look at the tweets in a two-dimensional space. You can actually do this with State of the Union addresses. So I take all these really high-dimensional vectors, one for each of the State of the Union address, and I can map it to a two-dimensional space. What that'll do is it puts each of my State of the Union addresses on a 2D plot. And the State of the Union addresses that had similar themes will be nearby each other. So I can start to visualize text as a graph, which is kind of cool. All right, so that's one. And then the other is clustering. Clustering is sort of the analog of classification, where, again, I do not tell you the labels. I just give you data, just x's. And your goal is to look at those x's. You know what? Those x's look the same. I'll call that group 1. Those x's look similar and different from these, but similar to these. I'll call that group 2, and so on. So you're inferring labels without ever seeing labels. So these are two forms or two genres of unsupervised learning. Again, sadly, we have not enough time to cover these. The good news is the tools for these are pretty straightforward, and you'll start to see that for a given application, there's a special set of tools that you will use to do either dimensionality reduction or clustering. All right, there's a third genre of the machine learning world that is pretty exciting, has recently become very exciting. Again, we don't have time to talk about it, but I just want you to be familiar with that. And this is reinforcement learning. It's a cool way of thinking about learning. So in the very far left of this picture, I gave you labels, and I say, just match those labels. On the far right, I give you no labels, and I say, just infer some meaningful labels for this data. In the middle, I don't give you labels, but I give you rewards. So you make a prediction, I go, that's pretty good. You make another prediction, I go, that's bad. And your job is to learn how to make good predictions. So when I say that's good, I didn't say that's the best thing you could have done. And in many cases, it might be good now, but it could be bad in the future that you made that decision. right? So this lets you reason about planning. So one of the big advances was AlphaGo. So AlphaGo is an example of using reinforcement learning to be able to beat humans at a very hard task of playing the game of Go. And the way that was learned is that you had computers playing against each other, and the only reward they got at the end was whether or not they won. Never said if any of those moves were good. Just at the end of playing, you did a good job. And the learning algorithm has to infer what that means for each of the actions that it took. Hard. It's a hard problem. We have barely cracked the surface of how to solve that problem, which is why we're probably not going to cover it in this class. But if you're interested in that, again, stop by office hours or take the upper division machine learning classes. Okay, that was a quick overview of the big pieces. Now we're going to dive into classification. Classification is very powerful, and I will add that a lot of these techniques in here, and even some of the parts over here, will use the same ideas that we're going to cover today. So this is a good lecture, good material. All right, so kinds of classification. We talked about, so we're predicting a categorical variable. The simplest form of classification will say, oh, that's a binary classification problem. You are predicting 0 or 1. That's a spam, not spam. Sell, don't sell. So very simple categorical response variable. There's another class, or another type, which is multi-class classification. This is where you're not predicting one, but potentially many categories. So this could be image labeling. So I show you a picture and you go, that's a cat, that's a dog, that's a plane. So you're picking from a much larger space of potential labels. You might also use this for sentence completion. So as you're typing on your phone, a classification algorithm might be running, in fact, hopefully you're not typing on your phone, but when you do, as you're typing each word, it's looking at the previous part of the sentence and trying to predict the next word. The next word is one of many possible words it could choose from. That is a multi-class classification problem. The techniques we will cover in lecture today, you can use to make a very good next word predictor. All right, then it gets more interesting. You have things like structure prediction for classification. This is something like you write a sentence in English and it outputs a sentence in Spanish. Right? So we're not making a single prediction of a single word, but a sequence of words from a sequence of words as an input. Right? So we're predicting a bunch of things at once, and they all have to make sense. Right? You can't just jumble words based on the input sentence. There's a meaning to each of those words and a particular ordering or relationship between them. We're going to focus today on binary classification because that is the fundamental building block of all these other techniques. All right, so binary classification. So the first thing we should do is say, why can't we just use our squared error? So we go back to our loss problem. Now my y's are 0 or 1. That's kind of like regression. We have linear models, which we've mastered. If we're a computer scientist, we take hammers and just use them for everything. This seems like we should be able to just use least squares regression. So to show you why that would be a bad idea, I have a Python demo. So let's do that. Okay. So I have a fairly famous data set that's available actually as part of scikit-learn. It's called the Wisconsin Breast Cancer Data Set. And I would like to use this data set to build a classifier for whether or not a tumor is malignant or benign. So this data set has a bunch of different features about tumors. I'm just going to focus on the mean radius. So what is the average radius of that tumor? And based on that, is it malignant or benign? Before I jump into what it looks like, does anyone have an intuition of what I'd expect for this model? Yeah?
Bigger tumors are more likely to be malignant?
Yeah, so the tumor is really big. It's probably malignant. If it's smaller, maybe it could be malignant. If it's really small, maybe it's not malignant. It's more likely to be benign. So there's kind of a relationship between size, maybe even a kind of a linear relationship between size and whether or not it's benign or malignant. Benign or malignant is a categorical thing, right? It's a 0 or a 1. Is it benign or is it malignant? So this is a classification problem. So here's what the data looks like, the mean radius. I've plotted all my dots on top of each other. This is an example of overplotting, yeah. We can kind of see a pattern here. So here's mean radius. These are the malignant tumors. These are the benign tumors. So they were 0s and 1s. We can transform this plot a little bit. So this is called jittering. I don't know how I feel about jittering as a plotting technique. It's lying, but it does make it a little easier to see what's going on. So what I've done here is I've taken the labels and I've added random noise to them. So I added a random noise to 1 and a random noise to zeros. And now you can see the cloud of points. Their meaning on this axis is meaningless. These are all 1s, but I've spread them out a little bit just so you can visualize them. This is, let's say, a reasonable technique to kind of diagnose data. I wouldn't publish this in a paper because it's a bit misleading. My label is either 1 or 0 and nothing else. But I've added noise to see what this data looks like. So we start to see a pattern. There's like a clump of points here that appear to be pretty benign. And then we have some spread, again, a clump of points here that are malignant, and then spreads out to some points over in the tail here. All right, a better way to visualize this, how I would put it in a paper, would be to show some histograms. So here are the two distributions of the benign and malignant tumors as a function of size. And we start to see a pretty clear pattern here, right? If you were looking at this picture and say, I want a model, I want a rule to decide if a tumor is malignant or benign, what might you do? Here, I'll slide to the right and you say when to stop. I'll do it again. Stop. Yeah, okay, good. Yeah, so this seems like they cross over. That must be the point, right? So just eyeballing it, you kind of have an idea of what a model might be. I want to think that if you're to the left of that spot, it's probably benign, and if you're to the right of it, it's probably malignant. Right? But we want a more formal way to build that model. So let's see how we could do that. All right, so we could do least squares regression. Before I do anything, I make a nice train test split. Today I will probably never look at my test data. Oh well. So I took my train test split will actually split a data frame. So I took all my data and I split it into a training data frame and a testing data frame. And I took out just the mean radius as my x value. My y value is my malignant or not. It's a float. And I'm going to fit a linear model. No cross-validation, no regularization, just a vanilla linear model. All right, so here's my fit. There's my model. Do we declare success? It is a linear model. It goes through some of the points. It does capture the trend. As I go right on that model, it's going to say more to the 1, and if I go to the left, it's going to 0. I don't know what to do about this. This says, if the tumor size is 25 millimeters, it is definitely a 1.51, which is not a reasonable value. It either has to be a 0 or 1. But we could work with this, right? So if I just gave you this, say, look, you got to make a rule with this benign or malignant, how would you do that? Let's do it again. Stop me. Stop. Like right here, how about when it crosses 0.5? Right? So if it's greater than 0.5, y is greater than 0.5, it's definitely malignant. If it's less, it's definitely benign. So definitely seems a little bit odd because, I'd like to have some notion of uncertainty. But it's at least a start, so I have a model. I'd like to treat it as a probability because I do want that notion of uncertainty. So what could I do to fix that for this picture here? So between here and here, that's a probability. It's between 0 and 1. What else could you ask for? Up here and down here, it's not a probability. We could do some corrections. How do I have this here? So here's what happens if I use this loss before I correct for probability. So here I could choose a decision rule and say, look, when it crosses 0.5, I'm going to classify everything to the left of here. So these are now determined to be benign. That's wrong. They're malignant. These are determined to be malignant. That's correct. But these are also malignant. They're not. They're benign. So I make mistakes. That is my basic decision rule for the least squares model. We have something called the 0-1 loss. So 0-1 loss is, did you get it right or wrong? It's not in regression. We had these squared losses. We actually looked at a bunch of different loss functions. 0-1 loss is kind of the ideal loss for classification. We want to get everything right. And so it's just a measure of how many things you predicted correctly. So here's my rule. I take my least squares model. If it's greater than 0.5, it's a 1. Otherwise, it's a 0. Y is a true value, 1s and 0s. 0-1 loss is just going to say, do they match? Right? Which fraction did not match is my error. So 0-1 loss is which fraction did not match. So I got 13% of my tumors misclassified, which is not bad. So we didn't do much thinking. We used what we already knew how to do, and we got a classifier that gets 13% error rate. That would be a little bit problematic that 13, and we should actually think about what fraction of the tumors looked like this, because that might make us a little bit worried. We're like, you know what, you don't have a malignant tumor. It turns out you did have a malignant tumor. We might not want to have a lot of these. These are a little problematic. They say we told the patient, look, you have a malignant tumor when it was in fact not. Hopefully we might do additional studies before we start treating that patient. So this could be dangerous if we went straight to applying some, let's say, chemotherapy. We have a basic model. We have some concerns about how it fits. But we have at least this foundation of what we kind of wanted. Something we're missing is our uncertainty. Right? This model is not really capturing a probability, which we kind of like. So we could say, you know what, this could be a tumor, or this might not be a tumor. So we'd like to capture that information. All right, so 0-1 loss is a good measure of our prediction accuracy. Another point. So in this particular data set, the fraction of malignant tumors was 37%. So 37% of the tumors were malignant. So that means that if I just guessed always benign, I get a fairly accurate model. What would my error rate be if I just always said benign? All tumors are benign. 37, right? So it's not 50-50. This is a slightly biased data set, it has a label bias, or unbalanced data set. And so I have to worry about that a little bit. Just because I have a low error rate doesn't necessarily mean I'm making good predictions. It could be I'm just guessing the more common class. All right, so this is an issue of class imbalance. I think I'll come back to that in lecture, so I might hold off on talking about it now. I'm going to skip 0-1 cross-validation. Let's jump to something a bit more interesting. All right, so one thing we could do is truncate our line. So we could say, look, if it gets lower than 0, make it 0. And if it's higher than 1, make it 1. This would move us in the direction of having something that's a little bit more like a probability. So this is this green curve here. This is my new model. And now I'm going to, let's pretend it's a probability. What does that do for us? So it says once you get to this point over here, we're 100% sure that that is a malignant tumor. And once you get to this point right here, we're 100% sure that that is a benign tumor. In this range, we're assuming there's this kind of linear relationship. So here, it could be malignant. At this point, it's a 50-50. And then over here, it's likely to be benign. Right? So we did get something that kind of at least behaves what we'd like of a probability. It's a number between 0 and 1. It does sort of reflect our uncertainty. But there's still some issues with this approach. All right, and so one of the issues that I want to talk about is when we use a linear model, the loss that we're trying to minimize is essentially trying to fit these data points to this line in the squared error sense. At least that's what we're doing here. And that could be really bad in the following way. So I'm going to imagine I have a 100 millimeter tumor. See, I have the picture over here. Good. So here's my tumor. It's 100 millimeters. This is a massive tumor. Okay, so I add that to my data set, and what does that do to my model? So this was my original least squares model. This tumor is, it's definitely malignant. I put it in the right place. I added this extreme outlier that's a reasonable outlier. And what did it do to my model? It actually skewed my model pretty substantially. In some sense, it pulled over what I think is malignant pretty far to the right, which means that now I'm classifying all these things as benign as well. So a data point that's really consistent with the patterns in my data is actually making my accuracy worse, right? Because the linear model is trying to minimize the distance between this line and that data point, that residual, not trying to match these probabilities. So everyone see what's going on here? Yeah? All right, so we'd like a better way to model probabilities. We'd like a model that captures explicitly our uncertainty. We probably want a loss function that's not the squared loss, but one that tries to match these probabilities directly. One that's going to give us a model that at the end of the day we can think of as a measure of our uncertainty about that particular label. All right, so let's do that. So back to classification. All right, so we saw that if we just take the squared loss, we're going to run into some issues. We get these extreme points. We could actually do some interpolation, which I didn't show in the previous slide. But it's possible that I could take a bunch of line segments at different points in my data set and get something that looks a little more like a probability. But we want a better model than that in general. So the answer is yes, in theory we could use this squared loss, but it has some big problems. We'd have to introduce that decision function, have to crop our probabilities if we want to treat them as probabilities. We really can't actually treat them as probabilities because we didn't learn them in that way. So it'd be difficult to interpret. And it becomes very sensitive to outliers. In this case, it's weird because it's an outlier that's very consistent with our data. And yet it actually makes the model much worse. All right, so we shouldn't use least squares regression for classification.